In this lecture, we'll look at how to simplify cube roots. Here we'll use the property that when we take the cube root of a product of factors, that's the same as taking the cube root of each factor separately and then multiplying. In our first example, we'll simplify the cube root of 250. If the number inside is not a perfect cube, then we want to see if there are any perfect cubes that are factors of this number, so that we can split it up and take the cube root of those factors separately. So we can go through this list of perfect cubes and see if any of these numbers divide evenly into our given number. In this case, the first three perfect cubes do not divide evenly, but 125 does. 250 divided by 125 is equal to 2. That means that we can write 250 as the product of 125 times 2. Now we can use the product rule for radicals. It says the cube root of 125 times 2 is equal to the cube root of 125 times the cube root of 2. So we'll be able to simplify the cube root of 125 because this is a perfect cube, and we'll be left with a 2 on the inside of the radical. The cube root of 125 is equal to 5, as we can see here. So we get that the cube root of 250 is equal to 5 times the cube root of 2 when we simplify. And this cannot be simplified any further because the number that's left on the inside has no more perfect cube factors. Let's look at the alternative method for this example, where we write this number as a product of prime factors using a factor tree. For the factor tree, I first divided 250 by 2. That gave me 2 times 125. 125 is not divisible by 2 or 3, but it is divisible by 5. We get 5 times 25, and 25 is 5 times 5. Therefore, we rewrite 250 with its prime factorization, 2 times 5 times 5 times 5. And for cube roots, we're looking for any 3 of the same factor. That will give us a perfect cube. And the cube root of 5 times 5 times 5, or 5 cubed, is equal to 5. So when we simplify, this will come out of the cube root as a single factor of 5. So the 3 factors of 5 on the inside becomes a single factor of 5 on the outside, and we're left with a factor of 2 on the inside. Notice that this 5 to the third power is the same as the 125 that we have here in the first method, and we're just taking the cube root of that separately to get the 5 on the outside. Now let's see what this will look like when we have variables. In this example, we're going to simplify the cube root of x to the 5th power times y to the 6th power times z to the 10th power. Let's start with the alternative method, where we write the product of each of these variables for the corresponding exponents. So we have a product of x 5 times, y 6 times, and z 10 times. Now we want to identify any products of 3 of the same factor. Each of these products of the same 3 factors will be a perfect cube. This is x cubed, y cubed, we have another y cubed, and we have z cubed 3 times. And remember, when we take the product of each of these perfect cubes, we'll get a single factor of that variable on the outside of the radical. So the cube root of x cubed is equal to x, the cube root of y cubed is equal to y, and we get 2 of those. The cube root of z cubed is equal to z, and we get 3 of those. On the inside, we still have 2 factors of x and 1 factor of z. So now we can simplify this. We have x times y squared times z cubed on the outside, and we have x squared times z left on the inside of the cube root. So this is the simplified form of the radical that we started with, after we factored out all of these perfect cubes. Let's look at a shortcut like we did for the square roots, because when these exponents are large, this method is not very practical. Remember that when we were looking for perfect squares, we needed to be able to write the expression as something to the second power. And if we have an exponent here on the inside, we would simplify by multiplying that exponent by the 2 on the outside. And that means that if a variable raised to a power is going to be a perfect square, then the exponent must be a multiple of 2. And now we can do the same thing for perfect cubes. To be a perfect cube means we need to be able to write the expression as something raised to the third power. And when we have an exponent on the inside, we would multiply that exponent by the 3 on the outside. And that means that a variable raised to a power will be a perfect cube when that exponent is a multiple of 3. And we can see that the cube root of any of these perfect cubes will be the expression on the inside of the parentheses here on the left. And we can get these exponents by dividing the original exponent by 3, which we can do when the original exponent is a multiple of 3. So the shortcut is that when we have a perfect cube, which means we have an exponent that is a multiple of 3, we take the cube root by dividing that exponent by 3. So the cube root of x to the 12th is x to the 12 divided by 3, or x to the 4th. So let's see how we can use this shortcut in our example. In this example, we had 3 variables with exponents. Only one of these is a multiple of 3, y to the 6th power. So that's a perfect cube. And notice when we simplified this, we ended up with a y squared on the outside. That exponent of 2 comes from taking the original exponent of 6 and dividing by 3. The other 2 variables have exponents that are not multiples of 3. So we need to factor those in order to get perfect cubes. First, let's try factoring out just one of each of these variables, like we did with square roots. When we factor out one factor of x, we get x to the 4th times x to the 1 equals x to the 5th. And when we factor out one factor of z, we get z to the 9th times z to the 1 is equal to z to the 10th. And z to the 9th will be a perfect cube because the exponent 9 is a multiple of 3. But x to the 4th is not a perfect cube because 4 is not a multiple of 3. So let's try factoring out 2 factors of x. When we factor out 2 factors of x, or x squared, we get x cubed times x squared, because 3 plus 2 is equal to 5. And now we have a perfect cube of x to the 3rd power. So simplifying cube roots of variables is a little bit more complex than square roots, because if we start with exponents that are not multiples of 3, we may have to factor out one factor of the variable, or we may have to factor out 2 factors of that variable to get a perfect cube. So you may have to try both, but you'll never have to factor out more than 2 factors of a single variable, because the exponent cannot be more than 1 or 2 values larger than a multiple of 3. So now let's rewrite this expression by factoring out the perfect cubes. Y to the 6th is already a perfect cube, so we don't need to modify that. X to the 5th will be factored as x cubed times x squared, and z to the 10th will be factored as z to the 9th times z to the 1. Here I've circled the perfect cubes. These are the variables that have exponents that are multiples of 3. And when we take the cube root of each of these, we will divide the exponent by 3. The cube root of x cubed is equal to x to the 3 divided by 3, or x to the 1 power. The cube root of y to the 6th is y to the 6th divided by 3, or y to the 2nd power. And the cube root of z to the 9th is z to the 9 divided by 3, or z to the 3rd power. you can see that we have an x squared and a z left on the inside of the cube root. So this gives us the same answer that we got when we wrote out the products the long way. Now let's end with an example that has both numbers and variables. In this example, we're going to simplify the cube root of 54 times p to the 8th power times q to the 15th power. Let's start by factoring out all of the perfect cube factors. First, for the number 54, we want to find the largest perfect cube that divides evenly. 8 does not divide evenly, 27 does, and 64 is already larger than 54, so 27 is the largest perfect cube that divides evenly. And 27 goes into 54 2 times, so we'll write 54 as the product 27 times 2. Now for the variables, we need to look at the exponents. A perfect cube will have an exponent that's a multiple of 3. So don't be confused by the fact that 8 as a number is a perfect cube. As an exponent, p to the 8th power is not a perfect cube because 8 is not a multiple of 3. So we need to factor out one or two factors of the variable p until we get an exponent that is a multiple of 3. If we factor out a single factor of p, we get p to the 7th times p to the 1 equals p to the 8th. But p to the 7th power is not a perfect cube because 7 is not a multiple of 3. So now let's try factoring out two factors of p. That gives us p to the 6th power times p to the 2nd power, and 6 is a multiple of 3. So this gives us p to the 6th as a perfect cube. So we go ahead and write p to the 8th power as p to the 6th power times p to the 2nd power. Q to the 15th power is a perfect cube because its exponent is a multiple of 3. So we don't have to factor the q to the 15th power. Now we'll be taking the cube root of each of these perfect cubes separately. The cube root of 27 is equal to 3, which we can see here because 27 is 3 to the 3rd power. The cube root of p to the 6th power is equal to p to the 6th divided by 3, or p to the 2nd power. The cube root of q to the 15th power is q to the 15 divided by 3, or q to the 5th power. And we're left with a 2 times p squared on the inside of the cube root. So this expression is the simplified form of the cube root that we started with. And we know that we cannot simplify this any further because the expression inside the cube root has no more perfect cube factors. Let's finish by simplifying this expression using the alternative method, where we write out the product of the prime factors and each of the variable factors. Here's the factor tree for 54. We get the prime factorization 2 times 3 times 3 times 3, which I've included here inside the cube root. Next I have a product of the factor p 8 times and a product of the factors q 15 times. And for this method, we want to identify any three of the same factors. Here we have three factors of 3, and the cube root of 3 to the 3rd power is equal to 3. For the variable p, we have two sets of 3 factors, so each of those comes out as a single factor of p. And for the variable q, we have 5 sets of 3 factors. So each of these comes out as a single factor of q. And inside the cube root, we're left with a factor of 2 and 2 factors of p. So this gives us the same answer when we simplify 3 times p squared times q to the 5th power times the cube root of 2 times p squared. Either of these methods will work fine, but the alternative method is not always practical depending on the size of the exponents on the variables. So it's good to understand this first method as well.